thank you. Well, firstly, I want to congratulate the organizers of this meeting. I think they've got together a terrific set of lectures. Well done. I think it's great. What I'm going to talk about is cosmology, and the first part I'm going to talk about is standard cosmology, what is absolutely standard. Then I will give some critical comments on standard cosmology, and if I have time, I will look at some issues that come from looking at it in a slightly broader context. Now, there's 3 separate review articles. I write a lot of review articles, which I might refer you to. Classical and Quantum Gravity, this is a Millennium Review article of mine called 83 Years of General Relativity in Cosmology, Progress and Problems. And this is a review, Classical and Quantum Gravity, on the state of cosmology. It'll be very similar to what I do, but it gives you a coherent view of that, which you can look up if you wish. Now, for the alternative cosmologies, I did a set of Cargier's lectures, which then got written up with Henk van Elst, and they're available on the web, so you can get them on the archive. I take it you all know how to get the archive. If you don't, you must ask some of the support people for this meeting. And this is a review of alternatives, of alternative models to the standard model. To start off, and I will say something about that during the course of this talk. Now, finally, there was a general relativity meeting in Durban about 2 years ago now, in which I did a critical survey of cosmology called The Status of Cosmology 2001, 2 Views and a Middle Way. Now, I will be giving you that particularly in the late afternoon session, when I will give a talk about it. But so what I want to say to start off with, this is called, as I said, 2 views and a middle way. Cosmology today, there are very conflicting views. There's a group of people running around saying cosmology is solved. All we need to do is fill in a little few details, and then we're done. There's a different view which I will make a case for in that afternoon lecture, whenever it is. It's on Thursday afternoon. There's a different view, which is that cosmology is pretty much a disaster because we don't actually understand any of its major dynamical features. And then the middle view is somewhere in between those, that it's a big mistake to believe that cosmology is solved. To say it's a total disaster, there are actually quite a good reasons for saying that, but that's also too far the other side, and that the real situation is somewhere in the middle. So this is just a brief sort of overview. So what I'm going to start off with is a summary of the standard model, because that's what I've been asked to do. And the standard model, it's known under various names: Friedman, F, Lemaitre, L, Robertson, or Walker. And these different names are used about it. Friedman is the Russian who first produced one of these models in 1922, and another one in 1924. Lemaitre, in 1927, was the first person who made these models kind of physically relevant. Friedman approached it mathematically, whereas Lemaitre approached it as a cosmologist, as a physical cosmologist. Robertson, in 1930 to 1933, was a person who pulled it all together and turned it into a kind of a coherent theory. In particular, what I will add to this, there's a very, very fine review article, H.P. Robertson, which is in Reviews of Modern Physics, 1933. And the basic features, the geometrical features of the model, standard model today, were already found in 1933. They can be found in this review article by H.P. Robertson. What has happened since then is a great deal more understanding of the thermodynamics, of the possible physics, and of the observations. But the basic geometrical structure and the basic field equation are already known by 1933. And then Walker, 1935 to 1944, Walker from 1935 to 1944 did some important work together with Robertson on the geometry of these models. And given the fact that nowadays there's a great tendency to look at alternative physics and to look at cosmology from sort of a viewpoint of quite a lot of alternative physics, the work of Robertson Walker is important because what Friedman and Lemaitre did was dependent on the field equations, but what Robertson and Walker did was not. It was independent of the field equations. So their work is very relevant to today's cosmology. So the first parts of these talks are going to be on the standard model, the Friedman, Lemaitre, Robertson. I guess I better write that down. Friedman, Lemaitre, Robertson, and Walker. And so you will find all these names associated with the standard model. So I've got 4 lectures plus the evening one. The evening one will be the critical review. The later parts of the sessions, if we have time, will be looking at the alternative models. But the main part is my brief is to look at the basic features of the standard model of cosmology. Okay, now, it has a large number of features which I'm going to go through in these lectures. And the first points about it, what underlies cosmology? What underlies cosmology is gravity. Now, because what underlies cosmology is gravity, what we need to use is general relativity, because that is the classical theory of gravity. Now, why is gravity the force that underlies cosmology? Because it is the dominant long-range force in the universe, and it dominates the solar system, it dominates our galaxy, it dominates everything on larger scales. The question you should ask yourselves at this point is to say, wait a minute, gravity is not the only large-scale force. Why is not electromagnetism the dominant force? Because, as you should recall from your fundamental physics, electromagnetism, you've been told, is a much, much stronger force than gravity. If electromagnetism is much stronger than gravity, why is gravity the dominant force and not electromagnetism? Well, the answer is, as far as we can tell, the total number of positive charges in the universe, the positive charges, is the same as the negatives. And this is a crucial feature of the universe. If this was not true, cosmology would not be dominated by gravity, it would be dominated by electromagnetism. But this equality of positive and negative charges has to be true to very high accuracy, because the electromagnetic force is so much stronger than the gravitational force. There have been people who have looked at possibilities of cosmology in which this was not true, in which there was a very, very small preponderance of either positive or negative charges. And those models are not believed, but you should keep asking yourself, why do we believe that in the scale of the solar system, the scale of the galaxy, and bigger scales, that there is the same number of positive and negative charges? Because if it wasn't true, then electromagnetism will dominate. Okay, well, having mentioned that possibility, I'm going to assume that equality, and because of that, we have gravity as the dominant force in the universe, and therefore we have general relativity as the theory that is relevant. Okay, now, what that means is that we will be dealing with space-time. So we will have 4 coordinates, xa, where a is 0, 1, 2, 3. It is 4-dimensional. Now, as you will know, in present-day physics, there's a great deal of stuff going on about 10 dimensions, 20 dimensions, 120 dimensions. The only space-time we have evidence for is 4-dimensional. Okay, it doesn't matter what you hear from anybody else in string theory or anything else. There is no proof that any of those other things exist. What we know exists is 4-dimensional. And that's what we will be dealing with here. Okay, so we have space-time with its 4 coordinates, it's 4-dimensional. We have a metric tensor. which depends on position in space-time. In special relativity, it's independent. In general relativity, it's dependent on position in space-time. Now, I've been told that you have all done courses in general relativity. What we get from the metric tensor is the interval. So I'm doing a very quick summary. What happens there is if you go along a path in space-time from a point xa to a point xa plus dxa, so you go along a displacement dxa, the interval assigned ds squared is given by the metric tensor and is given by that formula. And it's this interval which is important. If it is less than naught, then this corresponds to a clock measurement, and the proper time detour is the square root of minus ds squared. If this is greater than naught, it corresponds to a spatial measurement, and the distance, d capital D, is square root plus ds squared, and if this is equal to naught, it is motion at the speed of light, and represents motion of a particle moving at the speed of light, for instance, light itself. And so the set, when you have ds squared as 0, it defines the future light cone and the past light cone at each point in the space-time. So in a space-time, you've got the future light cone and the past light cone. Time-like vectors, motion at the speed of light, are in the interior, and so matter motions have ds squared less than naught, which corresponds to the speeds less than the speed of light, which we will take to be 1. So, you've got a space-time with coordinates, you've got a metric tensor. What does the metric tensor tell you? It tells you clock measurements. If it is less than naught along a displacement, it tells you spatial distance if it's bigger than naught, and it tells you that you're moving at the speed of light if it is equal to naught. Okay, now, from that, we determine the connection of the space-time, which determines the covariant derivative. And I'm just reminding you, I can't do all the details of this in this very brief introduction, but what this does for you in particular, it tells you what are geodesics. And a geodesic is a curve which is parallel along itself. And a geodesic is extremely important because a geodesic means motion under gravity plus inertia alone. Motion under gravity and inertia alone. If you're a geodesic, you are moving under gravity and inertia alone. For instance, the Earth moves around the Sun on a geodesic. The Moon moves around the Earth on a geodesic. The galaxy moves on a geodesic in the cosmos. And so any object which is moving under gravity and inertia alone will be moving on a geodesic, which is a curve which is parallel along itself. If the tangent vector is dxa by dv, then it satisfies the equation xa semicolon bxb, where that's the covariant derivative, is equal to naught. And that's a way of saying that the curve is parallel along itself. And in particular, light rays are geodesics, because light moves under only gravity and inertia, so light rays are geodesics, and the light cone represents the motion of light particles by which we see in the future and from which we can signal to the future. So I'm just saying all of this is just a brief summary. We're working with general relativity, so all of this is true. Now, the next thing we need is a stress tensor of matter and radiation and any fields which are present. And this tells you the total energy and momentum of all particles present. And from this, we solve the Einstein field equations. The Ricci tensor minus a half the Ricci scalar times the metric is equal to the gravitational constant times TAB. And these equations, the Einstein field equations, are what determine the metric tensor of the space-time. And you can, if you want to, add in a cosmological constant. And the cosmological constant, lambda, has been the source of debate ever since Einstein introduced it in 1917. Einstein produced the cosmological constant because he wanted to have a static space-time model, a static universe. Why did he want a static universe? Well, in 1917, everybody knew that the universe was static. It was unchanging. Okay, all the greatest physicists of the time knew in 1917 the universe was static. When Einstein realized, due to the evidence and other people's work, that the universe was expanding, he said, throw it out. We should not have the cosmological constant. From time to time, it has kept coming back. And as we will see towards the end of this lecture series, today there is evidence that there is a cosmological constant. It's not a big one, it's a small one, but that there is nevertheless a cosmological constant. So if you want to do cosmology today, you must allow for the possible existence of a cosmological constant. Okay, now, the crucial further point is that we need equations of state for our matter. Because the way the universe behaves depends on the equations of state. And to have a stress tensor by itself doesn't tell you very much. You need to know how the matter is behaving. Is it pressure-free matter? Is it radiation? Is it a scalar field? Is it an elastic body? Or whatever. So this is the start, the grounding point for all of this, is that we have got, in a cosmology, we're going to be dealing with gravity, which means general relativity, and you are supposed to have all done courses in general relativity. We have a space-time. We have a metric tensor, which tells you time-like clock measurements, space-like distances, and null, the speed of light. That determines the connection, which determines geodesics, which are curves parallel along themselves. That's their geometrical characterization. Physically, they mean motion under gravity and inertia alone. So, for instance, the Earth moving around the Sun, the Moon around the Earth, or the galaxy in the cosmos itself, all move on geodesics. A geodesic is parallel along itself. This is the covariant derivative of the tangent vector in the direction x. And light rays move on geodesics. This is the equation which determines the space-time curvature and hence determines the space-time metric. And one of the great things, the amazing things that general relativity did was to come to this realization. Until Einstein, the metric tensor, it wasn't expressed in this way, but essentially until Einstein it was assumed the metric tensor was a constant, it couldn't be a function, and that it was fixed, and it was fixed in some sense non-physically. The huge thing Einstein did was to say, no, the metric tensor is determined by the field equations. That means geometry is part of physics. That's a really amazing thing which Einstein said when he introduced the field equations. He was saying the amount of matter in the universe determines the curvature of space-time as expressed by the Ricci tensor and its contraction, the Ricci scalar. And that then is the way that matter determines curvature and so determines the metric. So geometry was brought into physics by Einstein's great discovery there. Okay, now, in cosmology, this was a very, very brief summary of general relativity, which I have to assume that you know because we don't have time to deal with that as well. In cosmology, there is one extra feature which is very puzzling when you first realize what it is. And the extra feature is that there is a preferred fall velocity in the universe. Now, this is very puzzling because you're told in general relativity that there isn't a preferred fall velocity. In some sense, the whole point of it in using tensors is that there is no preferred fall velocity. And now we're told there is a preferred fall velocity. And what we've got here is a classic case of a broken symmetry in physics, and you'll be hearing more about that from Professor Z. The field equations have the symmetry that any coordinate system is equal to any other coordinate system. That's general. But when you come to specific solutions, there are indeed preferred four velocities. And that preferred four velocity will be UA. It's a unit time-like vector. In other words, its magnitude is -1. So in the universe, represented like that, there are preferred motions of matter in the universe with a four-velocity vector field UA. And it is a major feature of the cosmos that all velocities are not equivalent. There are preferred velocities. How do you measure that preferred velocity? Well, it represents the average motion of matter. And as soon as you have matter, you can ask what is average motion. So you can form a big box around us. You can have a box big enough to include our galaxy, the Virgo cluster, the Coma cluster, and you measure the masses and velocities and you work out an average velocity. And so that's, if we do it carefully enough, that's a well-defined number, a well-defined vector, and that's the average motion. Nowadays, it is determined in a very, very precise manner indeed from the cosmic background radiation, CBR, cosmic background radiation, which we will be talking about at length, the 3-degree Kelvin black body radiation, which is the remnants of the hot Big Bang phase of the universe. The Nobel Prize for the work done in 1965, Penzias and Wilson, the discovery of the cosmic background radiation, black body radiation at 3 degrees Kelvin. And the point about this, it is 3 degrees, well, it's 2.75 actually. We'd say 3 degrees, it's 2.75 degrees. It is isotropic to an incredible accuracy, but at 1 part in 1,000, delta T over T, at 1 part in 1,000 is non-zero, and that is because of our motion of our galaxy relative to the cosmos, or relative to the background radiation. And if you measure that microwave background at 1 part in 1,000, the sky is hotter in one direction in the sky than the other. Now, the way we understand that is that this is because of our motion at about 300 kilometers per second. We are moving at 300 kilometers a second relative to the background radiation in the universe. And when you take out that motion, get rid of that motion, then once you've taken that out, then take it out, subtract that motion. In other words, change your reference frame to one where you take out that. Then delta T over T is of the order 10 to the minus 5. An incredible accuracy, and one of the most important figures in present-day cosmology is the fact that the temperature of the microwave background is isotropic to 1 part in 10 to the 5th once you've taken out the dipolar, which is 1 part in 1,000. And so the way that this is understood today is that we are moving relative to the microwave background at a speed of about 300 kilometers a second. And if you take that out, you get left with the isotropic of 1 part in 10 to the 5th. Well, that's something I'll talk about later, but for the moment, this is the important part. What this is determining it's determining a rest frame for the universe. And it's determined by the radiation coming from the hot Big Bang at the time of decoupling of matter and radiation. So there is a preferred motion, and it's very accurately determined. It's accurately determined to a few kilometers a second. So what we've got in cosmology, we've got all the apparatus of general relativity, which I've very, very briefly summarized here. But in addition to that, there is a preferred motion. And we talk about people moving with that preferred motion as fundamental observers. You're a fundamental observer if you're moving at that 4 velocity. On this planet, we are not quite fundamental observers. We are moving at this speed relative to the universe. Okay, now, I don't have time to go into a lot of the calculational details. So I'm going to immediately go on from this and talk about the second main point about the universe. This was just my little introduction to general relativity and to the single most important feature of cosmology, this preferred 4 velocity. What this means is we will always work out what happens relative to this preferred 4 velocity. Okay, now, the symmetry and the geometry of the universe are now the next points. What can we think about its symmetries and about its geometry? Okay, now, it is isotropic, the universe is isotropic about us to very high accuracy. We've just seen for the microwave background, it's 1 part in 10 to the 5th, an incredible accuracy. Now, since cosmology seriously started in about 1917, roughly then, cosmologists have been looking in all directions to see if there is anything different about the universe. It's not just the microwave background radiation, all observations are isotropic if averaged over a large enough angular, distance scale. Now, if you look at the night sky from Sutherland, you will see the band of the Milky Way covering the sky. So you say, wow, that's not isotropic. Actually, if you look out this window, you see all these buildings. That's not isotropic either. Isotropic means the same in all directions. Same in all directions. So look on a slightly larger scale. Look at the scale of the local cluster of galaxies. Well, that's not isotropic either. Look on a slightly bigger scale. You get the Virgo cluster and all of those. It's still not isotropic. The claim is, if you look on a bigger scale, and Professor Farrell can tell you a lot about this, he will be talking to you later on, average on a large enough scale, something like 200 megaparsecs, something like that. From that scale up, not below, but from that scale up, everything looks the same. Once you've hit that scale, we see, as we look in different directions of the sky, we don't see anything special. We have got no point in the sky which we say is the center of the universe. So if someone says to you, wow, where is the center of the universe? And the answer is the universe does not have a center, because we haven't seen anywhere which is very, very different from anywhere else. Now, these are the observations we make, and what we now do to make progress in cosmology, we make what is called a Copernican assumption. And the Copernican assumption is, well, in the old days we would have said we're not at the center of the universe. Nowadays we phrase it usually to say we are typical. We have no reason to believe that we are different from any other observers. In other words, if you went over to the Virgo cluster and looked around, you'd also see a pretty much isotropic sky. And so if we are typical. If you put this together with that, what we deduce, putting together the isotropy and the idea we're not typical, is all observers will see isotropy to very high accuracy, and it is then a mathematical theorem. It is then a mathematical theorem that the universe is spatially homogeneous. It's in a mathematical theorem that the universe is spatially homogeneous, and this is what Walker proved for us. In fact, was this mathematical theorem. So the argument is as follows. We look around on a large enough scale, and you see radio galaxies, you see quasi-stellar objects, you see X-ray sources, you see all of those things. If you look on a large enough scale, you see the same kind of thing in every direction in the sky that you look. So it is isotropic about us. In particular, the microwave background is isotropic to an extremely high accuracy. So what we say to ourselves is, look, there are basically two possibilities. The one possibility is that we are at the center of the universe and everything is made in concentric shells around us. Now, that's a possibility. It is possible we are at the center of the universe, and the reason for the isotropy is that everything is built in concentric cells about us. That's possibility A. Center of the universe. Okay, now, this was what everybody believed until about 100 years ago. Everybody believed we were at the center of the universe. until 100 years ago. Nowadays, we believe we are typical, not at the center of the universe. If we're typical, then everybody sees things isotropic, and you can actually see the way the proof works in the following way. If both A sees it isotropic and B sees it isotropic, then for A, let us suppose there are shells of density varying with distance going out. But for B, the same argument will hold. So for B, there are also shells of varying density. And what you see is his shells of varying density intersect with his ones. Now, the only way that can be consistent is if the density of all those shells is the same. In other words, isotropy everywhere implies homogeneity. So I've given you a very simple geometrical argument. If both A sees isotropy and B, what that means is the worst that can happen for A is inhomogeneity with spherical shells, but the same is true for B. But the problem then is his shells intersect with his. So A says the density is the same everywhere on that shell, and B says it's the same everywhere on that shell. Well, that means, if you think about it, that then A can say, but it's also the same on that. Once you know it's the same on these two shells, it extends to everywhere. The density must be constant in space. Okay? And from the space-time viewpoint, what it means is there is a preferred time, T. The pressure depends only on T. The energy density depends only on T. Anything you think of depends only on T. What is allowed is a time variation. Is allowed. And so the standard model of the universe is based on this simple line of argument. We see isotropy. If we are typical, if we're not at the center of the universe, then everybody sees isotropy, and that means the universe is spatially homogeneous and isotropic about every point. So the universe is spatially homogeneous and isotropic about every point, and that is what defines the standard models of cosmology, the Friedmann, Lemaitre, Robertson, Walker models. Okay, the metric tensor. Now, I'm going to shortcut a long bit of argument to say as follows. The metric tensor can then be written, metric is minus dt squared, where this is this preferred time, plus a squared of t, the scale factor as a function of time, into d sigma squared, where that is a 3 space of constant curvature plus 1, 0, or minus 1. We get 3 possible cases. And if you write that out, we get, in the coordinates I like, we get as follows: dr squared plus f squared of r into d theta squared plus sine squared theta d phi squared, where f of r is sine of r if k is plus 1, is r if k is 0, and is hyperbolic sine of r if k is minus 1. And this tells you the metric of the universe. Some people use different coordinates for this 3 space, but this is the one I like to use. And I need to tell you one other thing. The 4-velocity vector is delta A 0, that it is 1, 0, 0, and 0. So this is the metric of the space-time, which I needed to give you to tell you what the space-time is like. And then to have a cosmology, I must tell you where the matter is going. And what this says, we have surfaces in space-time T is constant, and the matter moves orthogonal. It moves orthogonal to these surfaces. T is constant in the space-time. Okay. So, these are the standard models. That's their metric, and that's how they move. Now, A of T is a scale factor. What that means is everything scales with A of T. Everything. So if you look at the universe here at an initial time T1, where you have A of T1, and you have a galaxy there and a galaxy there, G1 and G2. Now, let time evolve, follow the universe through time, and you end up at a second time t2, and that galaxy will have moved there, and that galaxy will have moved there, and that will be the distance d1, and that will be the distance d2, and it follows from here that d1 to d2 scales as a at time t1 to a at times t2. All distances scale like that. So, the Virgo cluster is moving away from us. All the more distant galaxies are moving away, and everything scales with the scale factor A. Now, the question people always ask when they've thought about it a bit is, what about the solar system? Does the size of the Earth scale with A of t? What about the distance of the Earth from the Sun and so on? Well, this is true on cosmological scales. I already mentioned here this averaging scale. This is the averaging scale. So when you use this metric, it does not describe what happens on smaller scales. We need to do something more complicated for smaller scales. It is only true for scales at the averaging scale and bigger than that. So this does not say the solar system has changed in size by a factor 2 in the past 1,000 million years. It says on the cosmological scale, everything scales with this scale factor. Okay, now, let me just briefly explain about the space sections. If you analyze that, what you will find is what it is saying is the following. It's saying take a typical point in the space t is constant and go out a distance d and look at a sphere here when you've reached a distance d. And if you're used to dealing with these metrics, you will be able to read off from that. Start off at a point r is 0 and then end up at a point r. The area of the two-sphere you get is 4 pi a squared of t f squared of r times is 4 pi a squared of t f squared of r. Choose in your space sections an arbitrary point. This is a space-time diagram. This is now a space diagram. So here I'm looking at 3 space directions, x, y, and z. Start off at the origin of coordinates, go out a distance d and draw a sphere at that distance. So that means you go the same distance d in all directions, it gives you a sphere. From this metric here, it follows that the size of that sphere depends on a, the scale factor at that time. It depends on f, this function here, evaluated at the time. And this is the unit sphere, which has area 4 pi, which is where this 4 pi comes from. So that's the area. Now, let's look at a fixed time and go to bigger and bigger radii, and you get the following 3 cases. If we plot that as a function of r squared, of the distance from the origin squared. In flat space, area is proportional to r squared, which is a straight line in this diagram. So that is the case k is 0. As you go out and out, distance scales as this area scales as the square of the distance. This is what we all expect and know from Euclidean geometry. But these space sections can be curved. If k is minus 1, in fact, what you get there in the flat space here, you get a is proportional to r squared. In the negatively curved space, it's proportional to the hyperbolic sine squared of r. That means when you've gone out a certain distance in a negatively curved space, a sphere is bigger than it would have been in flat space. And as you go further and further, this gets worse and worse and worse. It's going to go up exponentially because in that hyperbolic sine there is an exponential. And so the size of spheres in a negatively curved space is much bigger than you might have thought. In a positively curved space, the area is proportional to sine squared. And that is less than r squared. Not only is it less than r squared, it reaches a maximum and then goes down to 0. So in a positively curved space, take bigger and bigger spheres, their area gets bigger, but then they come to a maximum, and they then start decreasing and come back down to 0. Wow, what is happening here? Okay, this is the same as the surface of a sphere. If you set out from the South Pole in a sphere and draw a circle, the circumference is 2 pi r in flat space, but it isn't 2 pi r on the sphere, it's 2 pi sine of r. And it reaches a maximum at the equator, and it then starts decreasing, and it goes to 0 once you hit the antipole. So this is a two-dimensional model. On the surface of a sphere, go out a distance r and look at the circumference of a circle. It gets bigger and bigger till it reaches a maximum at the equator, and it then starts decreasing till you get back to 0. And that's exactly the same that happens here. What you've got here is your origin, and here is the antipodes, the other side of the universe. Now what happens on the Earth? If you keep going through to the South Pole to the north, keep going, what happens is you arrive back where you started from. If you play around with these spheres for a bit, you will see the same thing happens. Keep going and you reach your antipodes. Keep going, it gets back to 0, and these 2 points must be the same. They are necessarily the same in a surface of constant curvature. So in a surface of constant curvature, it's like the surface of the Earth. On the surface of the Earth, set off in any direction, keep going, you reach your antipodes, keep going, and you arrive back from the opposite direction. If the universe is positively curved, if you set off in that direction and keep going, eventually you'll come back through that wall and end up back here. And that's the same if you go up or over there or any other direction. Surfaces of constant positive curvature are closed universes, and consequently they are finite. Now, these two ones here are what we call open universes, and they are infinite. Now, this is a huge, huge difference, which people don't emphasize enough. In the case k is plus 1, because the universe is closed, there's only a finite number of galaxies out there. It's a very big number. So how many galaxies have we seen so far? Do you know? 10 to the 11 galaxies, roughly, we've seen so far. Okay. Now, in a closed universe, there might be 1,000 times that, 1,000 times 10 to the 11, which is a huge number, but it's a finite number. In these cases, if we have the natural topology, then the number of galaxies is infinite. The amount of matter is infinite. I'm emphasizing this because I don't think people think enough about the implications of infinity. We tend to think of infinity, an infinite number of galaxies, we tend to think kind of it's a big number of galaxies. It's nothing of the sort. It's a bigger number of galaxies than any number you can conceive. Okay. Think of any number and it's bigger than that number. And I'll return to this in one of my later talks. There are serious problems with the idea that the universe is infinite. People talk about it glibly in the literature, but there are serious problems with the belief that the universe might be infinite. Now, I need to add in a statement here that k is 0 and k is minus 1 are infinite in the natural topology, in the topology you first thought of. Euclidean space, if k is 0, this is in fact Euclidean space. And Euclidean space has a natural topology in which if you keep going that way, you just keep going forever. That's Euclidean topology. But for k is 0 and k is equal to minus 1, it is possible the universe is closed, even, and that it will have a unusual, let's call it an unusual topology. So the statement is as follows. If k is plus 1, the universe is necessarily closed. If k is plus 1, there's no option. The universe must be closed. But if k is 0 or minus 1, I've described for you the geometry. It's given to you by this metric. But this is a local metric. There's no claim that this is the global metric necessarily. And globally, it could have a different connectivity. And a connectivity is what we can call an unnatural topology. E.g., a torus. Torus is the simplest example. If the universe was toroidal, there would be a distance d1 and a distance d2 and a distance d3. Let's say that would be 600 megaparsecs. That might be 300 megaparsecs, and that might be 300 megaparsecs. Okay? So this is with flat spatial sections. With flat space sections, it could be a torus. How do you get a torus? You simply identify those two sides. You identify the front and the back, and you identify the top and the bottom. You identify them. So it then becomes like Pac-Man. You walk out that edge, and you walk in the other side. Okay? And it is possible that the universe has such a compact topology. Now, the point about this is the following. The Einstein equations give you the local geometry. They do not tell you the global connectivity, the global topology. And the flat space sections are just as consistent with Einstein equations as a torus. Now, if you lived in a toroidal universe, what would it mean? It would mean light from our galaxy would exit there and re-enter here. It would mean we would see our own galaxy over there, and over there, and over there. We would get many images of our own galaxy in a toroidal topology. And these are what we call small universes. A small universe is one in which we are able to see right around it since the decoupling of matter and radiation. And in a small universe, we will see many different copies of the same galaxy. So you might say, that's easy. Why don't we just look around and see if we see many images of the same galaxy? Well, why is that difficult? Well, because our galaxy is a typical galaxy. There's 10 to the 11th other galaxies out there. Suppose there was 1,000 images of our galaxy out there. How would you tell that it was our galaxy rather than a different galaxy? You would find it very, very difficult. The position is like, in this room, if we had glass on the ceiling and the floor and all the walls, you would see yourselves stretching away for infinity. The further ones would be dimmed by reflection in the glass. They would look much smaller. In the case of the universe, there's redshift effects and so on. And also, if you look at the different ones, you see yourself from a different direction. You would see your eyes in that direction, and the back of your head's in that direction, and the top of your head's in that direction. You would see yourself from all sorts. Yeah?
Sorry, how's that different from going this way and writing back from the other side? In the previous model, in a closed universe.
That's what. How's it different? Oh, it's the same.
Okay, so you can have the same effect as a closed universe.
Yes. Excepting the closed universe with the standard dynamics, the light doesn't have time to go around. In the standard dynamics, in fact, it's very finely balanced. In the K+1 models, in principle, you're quite right. But the problem is the time for light to traverse the universe is exactly the same as the age of the universe. So in those closed universes, we don't see around because the universe hasn't existed for long enough. Good question. So in the closed universes, if you had a static universe, Einstein's original static universe, then you had a sphere and the universe wasn't expanding. In that, we would have seen ourselves millions and millions of times because light could have traveled around millions of times since the beginning of the universe. In an expanding one, it's just delicately balanced. So just at the time you would have seen around, you hit the Big Bang and there isn't time for the universe to light to go around. Okay, so what I'm saying is the following. K is +1 implies compact. K is -0, -1. It is possible to be compact or to be finite. And you may have seen in Nature about 6 weeks ago now, there was a suggestion, faint suggestions from the microwave background that our universe could be closed in exactly this way. Let me say the following. For the case K is +1, there are alternative topologies also. There are also alternative topologies in the case K is +1, The natural topology of the sphere is you set off here and then you arrive at the antipodes, you keep going and you arrive back. Now, what's the simple alternative? The alternative, the simplest one, is when you arrive back at the antipodes, it isn't a different point, it's the point you started off from. That's a possible topology of the sphere, that each antipodal point is the same as the one you started from. Okay, now what I've done is I've spent quite a bit of time on the geometry of the universe and a little bit of time on its topology. I think that's about enough on that, except to say the final comment on all of this is that this is a very special situation. If, as a cosmologist or a relativist, you imagine universe models, all sorts of possible universes, what fraction of them would have this geometry? And the answer is a negligible fraction, because this is such an incredibly special geometry. And so one of the puzzles for cosmologists, most cosmologists believe that this is the geometry of the observable part of the universe. And I'll talk about limits on observations later on. So everybody believes this is a very good model. Well, not exactly Robertson-Walker, more or less. You've got this averaging scale. On smaller scales, it's not. But up to this scale, yes, Robertson-Walker. So the question which comes is why? Why on earth should the universe in which we live have this extremely special geometry, which is now being suggested by this metric tensor, with this universal cosmic time and with isotropy everywhere? So this is one of the puzzles which people have been looking. There are two schools of thought about this, and we'll come back to them later on. One school says, look, in general, we expect things to have a generic kind of behavior, and you write down random universes. This is infinitely improbable. And so we need to explain. We need to explain why. And the explanation is the theory of inflation, which I will talk about and other people will talk about later on. The idea that people now have, there's a theory called inflation, we'll talk about it later on, which tries to explain why the universe is as it is. But there's another school of thought which says, why not? Okay. In the old days, we didn't find it strange that the universe was special. This is the way it is. The mechanism that creates universes likes special universes. Okay? God likes special universes, nice symmetries, or whatever. Quantum field theory likes special universes, whatever it is. So, one group of people are asking why, but there's a small group of people who say the opposite, why not? And there is an interesting gloss on this. One of the underlying questions in cosmology is, why does life exist? Now, you may or may not think that's a question of cosmology, but if you pursue cosmology for long enough, one of the questions cosmologists want to answer is, why is the universe such that life can exist? And you can make a bit of a case that if the universe is not like a Robertson-Walker model, then life will not exist. So that's something I'll come to towards the end. One may be able to partly say one of the reasons the universe is isotropic and homogeneous is because it's very difficult for life to exist if the universe is not almost homogeneous and isotropic. Right. That was section 1. Sorry, section 2. The geometry of the universe. Now, 3. The size of the universe. Which I haven't mentioned so far, but we need to distinguish the universe or the observable universe. When people write about it, they often confuse these two things quite badly. The size of the universe is infinite. if k is 0 or minus 1 and the natural topology. You now understand that we have to add that criteria. So in a sense, so what's the size of the universe? If k is 0 or minus 1 and the natural topology is infinite. Well, people don't talk about it. When people talk about the size of the universe, what they're usually talking about is the size of the observable universe, what we can actually see. So please don't confuse these two things. They're quite different. Okay, well, this is about the scale of the inverse Hubble constant. We can see out, I'll talk about this later on, but basically we see out on our light cone, which goes back into time, and then the distance we can see stops when we reach the time of decoupling, which I'll mention because at earlier times the universe is opaque. We'll come back to this in half a minute, but at very early times, follow the universe back, its temperatures go up. In the present universe, atoms are atoms, but as the temperature goes up, they get ionized. The electrons get split from the nuclei because the temperature goes up so much. And so at very early times, the universe is opaque. How long do you want me to carry on for? Huh? Okay. Okay. The visual horizon is the distance we can see in the time allowed. The time light has to travel to us is not the time since the beginning of the universe, it's the time since decoupling. Because that's when the universe became transparent. And so following the universe back, at a time of decoupling, the universe became, which corresponds to a temperature of about 4,000 degrees Kelvin, the matter was ionized. That's ordinary physics. Once it's ionized, the universe is opaque because of Thomson scattering. So the universe was opaque and it became transparent. How far can we see out? Well, it's about the scale of the inverse Hubble parameter. And that is about 10 to the 10 light years. So the visible part of the universe is of the order of 10 to the 10 light years. Within that scale, there's of the order of 10 to the 11th galaxies we can see, which means there's of the order of 10 to the 22nd stars in the part of the universe we can see. Now, our scientific notation makes it easy to write this down. 100,000 million galaxies, each containing 100,000 million stars. How many planets are there up there? Wow. Any guesses? How many planets? Well, let's take a guess. 10 to the 26 planets. So how many people up there are there looking back at us? Well, it depends on the fraction of habitable planets, but 10 to the 26 planets, that's a heck of a lot of planets. Unless there is something unbelievably special about this planet, there's a heck of a lot of other things, people, whatever, up there looking back down at us. How many inhabitable planets? Who knows? Given these numbers, I could easily make a case for at least 10 to the 10 habitable planets up there. Sorry, this number was wrong, 10 to the 26 planets. Sorry, that should have been about 10 to the 23. So, what we've got then is this huge size, 10 to the 10 light years, and this huge number of galaxies, this huge number of stars up there. So a question which arises is why? Again, why is the universe so big? And this again is something which we say a little bit about later on, but it has enormously important implications for observations. Here we are on our planet up there, looking out at the universe. Now, let's say we get gung-ho about astronomy. Let's say we're going to set up a computer database and we're going to collect data for the next 10,000 years and analyze it in order to see the changes in the universe. So we start collecting the data up there and we look for 10,000 years. When will we be 10,000 years from now? The answer is we'll be at the same spot in the history of the universe because of the scale of 10 to the 10 years. If we set out in a spacecraft today, traveling at the speed of light for the next 10 to the 10th next 10,000 years collecting data. So we're moving sideways from here and we're trying to collect data. Where will we have got to? We won't have left that spot in the universe. In other words, because of this immense size of the universe, we can only see the universe from one space-time event. And that is one of the most fundamental features of observational cosmology. On the Earth, you can look and the horizon cuts you off. So you travel to the horizon and you look beyond the horizon. In cosmology, you're cut off by the horizon, so you say, okay, let's go and travel to the horizon. Boy, you can keep going, and you don't make any impact on the size of the universe. So the effect about this is that it's like trying to tell what the Earth is like from the top of a sand dune in the Sahara Desert, and you look around and you say, wow, the whole universe is made of sand dunes. Well, that's because you can't travel to the other parts because the scale is wrong. This little ant sitting there comes up with the theory of the Earth is made of sand dunes, and it follows exactly the lines of the argument which I've given here, the Copernican Assumption. Everywhere else must be what you see. Well, you can immediately see it ain't necessarily so. Okay? So although the bit of the universe we can see has got a particular kind of structure, the part of the universe we can see is limited to 10 to the 10th light years. And way out here, things could be completely different. In fact, chaotic inflation makes the claim that they are completely different out there. All right? So when we look at this business of the size of the universe, it raises a question of why, but it raises an enormously important question for observational cosmology. It's telling us the limits on what we can know about the universe. We can only know what is inside this little sphere. When I say little, 10 to the 10th years, compared with an infinite universe, that is a zero fraction. Compared with very, very large universes, that is a tiny fraction. I return to the small universes. The exception is the small universes. If by chance we were in one of those universes we've already seen around, then the situation is completely different. Then we have seen everything in the universe. Not only seen it, we've seen it multiple times. And in that case alone, we have complete observational access to everything that there is in the universe. You can begin to see why I say it's a really important question. Is the universe a small universe or not? It really makes a huge difference to our relation to the universe. Okay, on a slightly different kind of point about the size of the universe, people have continued to ask why it is so large, and the answer which is given today again is the same. It is the inflationary universe which has made it so large, as you're going to hear in other lectures in this course. And on the other side, I mentioned life briefly, the existence of life, of course, from a sort of human perspective. One finds here the incredible smallness of humanity in terms of relation to the universe as a whole. Now, as a cosmologist, one could have imagined a universe which is only 1,000 light years across, or was only 1 light year across, or fraction of a light year across. Thinking of the family of all cosmologies, it is a very important feature of the universe that it is as big as it is. It could have been very small, and it ain't. Okay. Now, evolution of matter in the universe is section 4. I'll carry on for about till about 1:15. I think you'll be pretty tired by then. Okay. In a Robertson-Walker model, you have the pressure, which is a function of time, and the energy density, which is a function of time. And what you need in order to describe the matter is equations of state. Equations of state relating the matter to the radiation. For instance, pressure is 0, which nowadays is called baryonic matter. Or pressure is a third mu, radiation. Now, what kinds of matter must we take account of? And this is really important. Cosmology is really tied into physics in a crucially important way. Okay, we know we've got baryonic matter. We know we've got radiation. We've got neutrinos. We've got cold, dark matter. There's a lot of evidence for that, which I'll mention a bit later on. We've got a cosmological constant. There's a question whether you should think of the cosmological constant as matter or not. But what you may have is scalar fields. That's a field phi, and associated with it may be a potential v of phi. And it is scalar fields which underlie the theory of inflation. So we better take them pretty seriously, because they are what dominates the very early universe if inflation is correct. So we've got baryons, we've got photons, we've got neutrinos, we've got cold dark matter, we've got scalar fields. That's a minimum that you need to take into account in a realistic look at matter in the universe. Actually, of course, it's much, much more complicated than that. You've got quarks and anti-quarks. But at the cosmological scale, we don't have to go into those details. We can use a phenomenological description in which we don't discuss the fundamental nature of it. We just use a large-scale approximation. Now, the two approximations, one is the kinetic theory description, and the other is the fluid description. In cosmology, we either use a kinetic theory or a fluid description. And I'm not going to go into the kinetic theory description here, but it's become very important in analyzing the cosmic background radiation. And if you go seriously into cosmic background radiation, you better learn kinetic theory on a curved space-time, which is quite a fun subject in its own right. But we'll use the fluid description, which is the continuum approximation. Now, when is a continuum description a good description? Well, you need a sufficient number of particles, is the first point. Sufficient numbers of particles, and I've said we've got about 10 to the 11th galaxies in the observable part of the universe. Is that enough for a fluid description? It's actually very marginal. In 1 cubic centimeter of matter, there's 10 to the 23rd atoms, much, much, much bigger than that. If you're talking fluid descriptions, this is really on the very low side for a fluid description to be good. On the other hand, the other alternative would be an individual particle description. You try to describe every particle in some sense. Well, that's hopeless with 10 to the 11th, so we certainly won't try that one. So we will use a fluid description, but remembering, actually, the statistics are not that good for a fluid description with only 10 to the 11th. The next thing you need is regularity. And what I mean by that is the following. Supposing you take a box of size L and you measure the density in there. Well, it's a function of the size L. And there are different possibilities. What we need is what happens for a realistic fluid as you vary the size is something like the following. On large scales, it's smooth, but on smaller scales, it starts fluctuating. Now, why does it fluctuate? Well, very simple. For a small enough box, as you change the size of the box, the number of particles in the box becomes just a few atoms, and each time you get 1 or 2 more atoms in, you get a wild fluctuation in the density of the box. So you need to be much, much bigger. You need to have a large number of particles in there in order to get this smooth description. At large scales, it starts varying because of macroscopic variations, and so there will be a set of scales on which a fluid description is a good description. I keep coming back to this idea of an averaging scale. So in cosmology, the idea is that there is a set of scales. Now, there are some universes in which there never is such a scale, and those are fractal universes. So the practical question we're being asked is the universe in fact fractal? And you will have seen many books out there saying, yes, the universe is fractal on all sorts of scales. If the universe was fractal on a cosmological scale, life would be very, very difficult for cosmologists. Now, there is a group of people who say it is fractal on that scale. There's a group of people in Rome who keep producing analyses who are saying, yes, it is fractal. However, most people believe it may be fractal on smaller scales, but by the time you hit this kind of averaging scale, that the universe is smooth. And that is critical in defining this 4 velocity. You can only define a 4 velocity if the universe has got a good averaging scale. Otherwise, the fluid description isn't possible and the averaging scale description doesn't hold. So we will assume that it is not fractal and that a fluid description is good. Then we can use a stress tensor, rho UA UB plus P HAB, where H is the tensor GAB plus UA UB. And that is the stress tensor for the fluid. Now, you put that into the conservation equations, and in this brief series of lectures, I don't have time to do the mathematics. You'll have to believe me, what we get out of that is the conservation equations. Rho dot plus 3, rho plus P, A dot over A is 0, that is energy. And the momentum equation will be naught is naught. It's identically satisfied. So in the context of the standard model of cosmologies, there is only one equation which matters for energy and momentum conservation, but it's exceedingly important. It is the equation of energy density conservation. Now, what you can do with this is you can put in some of these equations of state, like that or that, and see what happens. So, for instance, if you put in P as naught, you get rho dot plus 3 rho A dot over A is naught. So rho is a constant over A cubed, and that is conservation of baryons. If you put in P as a third mu, then you get rho plus a third rho, and that gives you a rho dot plus 4 rho A dot over A is naught, and you get rho is m over A to the 4th, and that's conservation of radiation. And the difference is very, very important. The difference comes from the P in the rho plus P there. As I say, I haven't got time to derive these equations, but that's what you get. Now, for radiation, rho is a constant times T to the 4th, and so put that together, the temperature is proportional to 1 upon A. One of the fundamental features of the expanding universe, as it expands, the temperature scales inversely with the radius. And so that's one of the absolutely fundamental things that happens in the expanding universe. For radiation, temperature goes down as 1 over A. And that underlies the whole hot Big Bang. Because, as I've already mentioned, we've got 3 degrees K radiation today. We'll follow the universe back. Well, when it was 1,000 times smaller, it was 3,000 K. When it was 1,000,000 times smaller, it was 3 million, and so on and so on. And so we have the hot Big Bang, follow the universe back. As A goes to naught, the temperature goes to infinity. And that is why all of fundamental physics comes into play as we follow the universe back to earlier and earlier times. Following it back, you get nuclear physics, particle physics, quantum gravity. They all come into play because of the conservation equations here. Now, what is very important is energy inequalities. And the one which I'll point out to here, for any ordinary matter, rho plus P must be positive. The energy density plus the pressure must be positive. Now, for ordinary matter, the density is positive and the pressure is positive. But we're going back to the very early universe when extreme quantum conditions were in control, and things could have been very, very different when those extreme quantum conditions were in control. The limiting condition is rho plus P is naught. Now, what happens if rho plus P is naught? Well, what happens is very strange. Look here. In that case, it doesn't matter how you expand the universe, then rho dot is naught, rho is constant, irrespective of whether the universe expands or contracts. So if you could ever find matter with rho plus P 0, it wouldn't be affected by expansion or contraction. Well, what is that? That is, in fact, the cosmological constant. Supposing you could find matter with rho plus P less than naught, what would happen then? Well, something very, very odd indeed. As you expanded the universe, the density would go up instead of going down. Not only that, but the momentum equation for perturbations would tell you. The momentum equation actually in general will be that dv by dt plus rho plus p times the, rho plus p dv by dt is equal to minus the pressure gradient. I'm writing it out in a rather cryptic notation. In relativity, the momentum equation is rho plus p dv by dt is minus the gradient of the pressure. And if you could find matter for which rho plus p was less than naught, what would happen because of this equation is you would push the matter this way, and in response it would go that way. Okay? If rho plus p is 0, that is matter where you push it and there's no response. Sorry, you push it and there's an infinite response. This is the inertial mass density. As the inertial mass density goes to 0, the same pressure gradient gets you a bigger and a bigger and a bigger response. And the response in this equation that diverges as rho plus p goes to 0. In other words, the same pressure gradient gives you larger and larger and larger response, diverging as rho plus p goes to 0. So if you have a theory of matter in which rho plus p goes to 0, you better watch out for velocity instabilities as that happens. And if it goes the other side, it will be totally non-physical, because when you push it this way, it'll go the other way. Now, there are some people trying to push this idea at the moment in cosmology. They are using the phrase shadow matter. Whenever you see the phrase shadow matter, you better worry about whether this is physics or imagination. Okay, we've had quite a session today. Where's Jeff? Should I carry on a little bit or stop? I think we stopped at this point.
If not, then... Oh, sorry. Yes.
Do you think there is input of energy into the system, or is it a closed system with no input at any time?
Well, the old steady-state universe, in a sense, was suggesting there was an input. In fact, that's exactly what it was. Fred Hoyle modified the equations of gravity to include a creation term, which was an input from outside. It is possible that that could happen because we can only test energy conservation to certain limits. And in the Fred Hoyle theory, you were only getting 1 hydrogen atom per cubic megaparsec per century or something like that. And it's a scale where it is incredibly difficult to test. So if anybody says to you, is energy and momentum actually conserved exactly, what you have to say is, well, experimentally, I can never prove it is exactly true. We have theoretical reasons for believing it may be exactly true to do with symmetries and theories and so on. But the standard view will be the system is closed, energy and momentum conservation is exact.
Any other questions? Okay, if not, then we should thank Professor Ellis again. And we're heading down to the Baxter Theatre for lunch. For those of you who have a car or something that want to get there, you can drive down to Baxter. The rest of us are going to walk. We're going to walk back up again. So just so there's a bunch of people who know how to get there from here, just follow them. I'm going down the road. Okay. So for those of you not walking, we'll meet again at the Baxter for lunch from about 12:30 onwards.
Okay, this was more or less what you wanted.
This is exactly what I wanted.
Okay, good.
So you're coming down to lunch?